go through some kind of roadblocks, but for now, let's enjoy it. This is sine 3x. I'm going to copy that over x. Well, this is a 0 over 0 case, so this is indeterminate form. So we can use L'Hopital's rule, saying you differentiated. What is that? Cosine 3x. Did I forget something? Yes, 3 for the chain rule. And the derivative of this one is 1. Now reevaluate this limit. Limit as x goes to 0. So this one is going to be 1. Cosine 0 is 1. So this is 3. We get the same answer, 3. Okay, so this is how we use L'Hopital's rule, because this is in the indeterminate form. Okay. The next one, number 19, limit x goes to 0, sine 3x over sine 6x. Well, let's go to just L'Hopital's rule directly. See, as x goes to 0, this is a 0 over 0 form, indeterminate form. So, the L'Hopital's rule says derivative of this, 3 times cosine 3x. Here is 6 times cosine 6x. Now, pause and rethink. Well, this is cosine 0, right? 1. Again, cosine 0, 3x or 6x, doesn't matter. Again, this is 1, so answer is 3 over 6, which is 1/2. Okay. Now from number 20, yes, no more limit problems, not much, okay? But yes, interesting differentiation case. I asked all of a sudden to differentiate this x to the x. X to the x, well, if you think this one as, okay, this is a power, so x times x to the x minus 1. Okay, I'm not sure if this is correct though, okay? Once you do that, you are going to say, oh, x times this, therefore, again, this is x to the x. The derivative of x to the x is the same x to the x. Well, the question mark is the very first step. We cannot differentiate as is. This is false. We can differentiate like e to the x. The base is constant. Or you can differentiate x to the third power. In this case, the power is, exponent is constant. Okay? If one is constant, then we can differentiate it. However, x to the x, well, both the base and the exponent, both are variable. In that case, we cannot differentiate it. So this part is wrong, and we have to avoid this one as like x to the x. So how do we separate this x and x over here? Is, yes, we are going to set y equals x to the x. We are going to differentiate it, okay? We are going to differentiate it. Well, we cannot apply regular differentiation, so we are going to take a log first. Take natural log. Meaning, we are going to say ln y equals ln x to the x. Now, interesting happens over here. Because x is a power, okay? So this one comes in front. So it becomes x times ln x. You see? So ln y equals x times ln x. We are going to differentiate it. What kind of a differentiation do you call this kind of a differentiation? We call it implicit differentiation. Implicit differentiation. Okay. Well, implicit because it's not straightforward y over here. anything x and y are mixed or just something other than y is there. Then we call it implicit function. Therefore, we have to apply implicit differentiation. Well, anyhow, our goal is find over here what is dy dx. That is our goal, okay? Finding dy dx. In order to do that, yes, we are going to apply d dx on both sides. So d dx, ln y. But the other side, d dx, x times ln x. See. So the first one, implicit differentiation. So you differentiate ln y, so that gives you 1 over y. But we have to differentiate with respect to x. So it's like applying the chain rule. So multiply by dy dx. Okay? The right side is you have to apply the product rule. So I differentiate the first one, 1 times ln x plus. Now differentiate the second one, which is 1 over x. So this is 1, this is ln x. Therefore, what we have over here is 1 over y dy dx equals ln x plus 1. Or I'm going to say 1 plus ln x, because I always want to separate this 1 from the natural log. Okay? So here, what is our goal? Our goal is finding dy dx. Don't forget that. So we are going to separate this one. So dy dx, we multiply both sides by y, so that makes y times 1 plus ln x. It doesn't look too good. Y is what? Y is x to the x. So dy dx equals x to the x times 1 plus ln x. So this is the derivative of x to the x. You see? X to the x. The function itself is in here and then multiply by this. Well, you are going to apply this kind of taking log first and then differentiate it for anything like, for example, x to the sine x. Okay? It doesn't matter. Again, d dx, x to the 4x. Anything, both part has this variable in it, okay? Then you are going to use exactly the same thing. And in this section, in L'Hopital's rule case also, it is just impossible to take just a limit directly. In that case, what I'm going to do, we are going to take a log first and then find the limit, okay? Of course, we have to make an adjustment after that, because we took a log, so we have to take it back. Okay? Well, number 21, easy. Y equals ln x. Ln x is this. Okay? When x equals 1, y equals 0. So x-intercept is 1. There is no y-intercept. Yes, this graph cannot touch the y-axis. Not at all. And this is, therefore, you can say immediately limit of ln x as x goes to 0 plus. What are they going to say? Yes, that is negative infinity. On the other hand, the limit of ln x as x goes to positive infinity, yes, it goes to infinity. It is very, very slowly rising, but it will rise to infinity. Okay, so this is what is implying, this graph implies over here. Yes, from now on, when you have a graph, not just a function value purpose, yeah, in order to just solve some limit problems, yes, if you know the graph, that is the fastest way to go. (22) Graph y equals e to the negative x. Well, the difference. Y equals e to the x. This is y equals e to the x. It's growing. natural, I mean not naturally, here is what? Exponentially growing. Okay? Exponentially growing. On the other hand, this is a decay model, correct? Okay? So decay model, e to the negative x, going like this. Okay? Right now, in the beginning stage, okay, early on, the coronavirus case, okay, confirmed patients, confirmed, positive people, well, is exponentially growing. Well, at some point, once they reach the peak, after that it's going to be decay. I hope this day comes faster than we think. All right. And this is what I emailed you when there were cases in China, okay, when China started to report about coronavirus cases. Yes, if you go back and check my email, the curve is exponential function graph. Number 23, y equals 1 over x. Well, why do we need this again and again? It's a very, very interesting case. Right in the middle of the graph, there is a gap, huge gap. One goes to positive infinity, the other one goes to negative infinity. Okay, it's a very interesting case, and this is the only discontinuity. Okay, so for example, if you have a graph problem like a negative 2 to 3, you integrate 1 over x. Looks like a very, not a big deal because the ln x, yeah, we have that absolute value of x, so you apply that. But this one is not working, okay? It's not that you don't have to, you don't even go there. From here to here is wrong because there is discontinuity, then we cannot integrate that, okay? But soon we are going to overcome that part. Still, we overcome, that means we are going to have a way to integrate it, but the result is meaningful or not, that is another story, okay? Number 24, y equals 1 over x squared. Kind of you expect the same thing from like y equals 1 over x case. Yeah, similar thing. As x goes to 0, yes, it goes to positive infinity. But from both directions. Earlier, what? You have 1 goes to positive infinity, the other side goes to negative infinity. But because this is x is squared, either way, it goes to positive infinity. The graph looks like this. And 25, yes. I showed you earlier y equals tangent x. Yeah, we can draw one more time. This is one complete cycle of a tangent function. So it repeats itself like this again and again. But to make just one-to-one function so that we can define the inverse trig function, inverse tangent function, we have to restrict the domain only from here, from negative pi over 2 to pi over 2. Okay? So, what is that? The graph is this. Going to positive infinity, going to negative infinity. Over here. Well, where is the next vertical asymptote located? You see, if you draw another cycle, there will be next vertical asymptote is coming. Well, that one is going to be add pi over here, 3 pi over 2. Why add pi? Because the function, it repeats itself every pi. Okay, that's why. Number 26, limit of tangent x. X goes to pi over 2 negative. Well, earlier we saw that one is infinity. Okay. Number 27, limit x goes to 0. 1 minus cosine x over x. Yes, this is another one that you kind of memorized in calculus 1 class. Yeah, earlier we did the limit sine x over x as x goes to 0 was 1. Here is another case, 1 minus cosine x over x. Yes, you remembered this one as 0, you memorized it. This time, we realize that, okay, as x goes to 0, cosine 0 is 1, so 1 minus 1 is 0, x goes to 0, so 0 over 0 case, which is what? Indeterminate form. That is a huge thing. Indeterminate form, that means we can apply the L'Hopital's rule. Okay? No other cases, only these indeterminate cases, indeterminate forms. So limit, everything stays the same. The limit x goes to 0, but now we differentiate it. 1 minus cosine x, the derivative of cosine x is negative sine x, so this is positive sine x. The derivative of x is 1. So now we regroup and evaluate the limit over here. What is sine 0? Sine 0 is 0 and 1 is 1. So 0 over 1 is 0. Do not keep just differentiating it. No. You always check, evaluate it, take the limit, and then look at this. Oh, 0 over 1 is 0. It is, you can determine what that is. Okay, so we can say we can stop right here. Okay. So as you see, we are going to have a lot of functions, different functions, and including trig functions. And I'm going to give you just a 2-minute heads up for the L'Hopital's rule. L'Hopital's rule is applied to a form of a quotient like this. So limit as x goes to something. It could be infinity also. Okay? If this is indeterminate form, and then we can say same thing. We say to the derivative without using quotient rule. We differentiate the following just individually, f and g, and we do this. Well, if this is again indeterminate form, what can I do? Yes, we can apply L'Hopital's rule 2 times, but you must realize this is indeterminate form. So, 1 over infinity, is this indeterminate form? No, this is 0. Yes, okay. What about infinity over 10? This is infinity, it's not indeterminate form. However, 0 over 10, what do you think? Again, 0 over 10 is 0. It's not indeterminate form. Alright? What about 6 over 0? Yes, this is infinity. It's not indeterminate form. So indeterminate forms are certain things. It has to be very, very physically clear. Infinity over infinity or 0 over 0. Yes, you are going to have more other cases like infinity minus infinity cases. Okay? Or 1 to infinity. It's interesting. Well, 1 to infinity, isn't this 1? But 1 is not flat 1. A little bit more than 1. That creates a big difference. Okay? So things like this. So these are the indeterminate form. Each indeterminate form, how we are going to find the limit, that one is going to be, well, the main topic for the next section. Okay? So see you soon. We are going to have a online class like this until the end of the semester. All right. Bye.